So here's kind of a classic example where we can apply Bayes' theorem, and that's in testing for some disease, some condition. We could do it with COVID. Things get complicated when we're in situations where you're getting tested because you have certain symptoms that may be indicative of a disease. So we're going to keep it simple for this example and assume that there's some genetic disorder uh, based on a random mutation unrelated to one's parents that occurs in one person per thousand, and that the only way to learn whether you have this disorder is through a diagnostic test. And we're going to assume that everyone's encouraged to take a free test. So, the choice of whether or not to get tested is not related to whether or not you have the disorder, right? Everyone's doing it, or to the extent that people aren't, it's not based on any symptoms. It's something that's going to happen some years in the future if you have it, that it'll result in some kind of physical manifestation. And so imagine that there's a diagnostic test that is really pretty accurate in the ways that you'd want it to be. It has a 99% detection rate. That is, for those with the disorder, there's a 99% chance the test will come out positive. Remember, positive means you have the condition. So that would be scary news, right? If this is a disorder, you don't want it. And if you get a test back and it says you're positive for the disease, one, would think that that is bad news. And as far as in that case, there's still 1% chance that if you have, even though you have the disorder, it incorrectly tells you you don't. It comes out negative. Now, separately, if you do not have the genetic condition, there's a 95% chance the test will come out negative. That's going to be happy news, right? It's correctly telling you that you don't have the disease. So there's a bit of a higher error rate among those with without the condition, right? So when you don't have the a genetic disorder, there's still pretty low chance, a 5% chance, but there is a chance that you are going to be incorrectly told that you have the disease. That is, you're going to be given a positive uh, outcome, positive test comes out positive, despite the fact that you do not have the disorder. Okay, so now, given you can see all of these really high accuracy rates, right? You summarizing, right? You have the disorder, there's a 99% chance that the test is going to say you do. If you don't have the disorder, there's a 95% chance it's going to say you don't, right? So my test comes up positive. How nervous should I be, right? Seemingly very nervous, right? Take a moment, maybe pause this, and try to intuitively tell me what you think the answer to this question is, right? Like, what's the probability of having the disorder given that my test came up positive? I go in, I have no reason to suspect that I have the genetic disorder or don't have it, other than that there's only a 1 in 1,000 chance that a person has it. And I get the test comes up positive. Given that it came up positive, what's my probability that I have the disorder? Okay, I'm going to do this via sort of decision tree. It's a bit more, most people find it a bit more intuitive than just plugging numbers into a formula. You can do that as well. And we'll see it both ways. So the probability of having the disease is 1 in 1,000, right? 0.001 tenths, hundredths, thousandths. So 1 in 1,000 chance. So this is like I'm born, rolling a die as to whether I have it or not. It's a 1,000-sided die. There's only one side that comes up disease and the rest not. Okay, and so D is the event of having the disease. D complement is not having disease. Okay, so conditional of having, we're going to be thinking about sort of moving down these possible paths, right? In the unlikely instance that I have the disease, I go get tested. There's some probability we want to analyze conditional on having disease. What's the chance test comes positive? What's the chance that it comes up uh, negative, right? Positive complement seems a little bit silly. So let's just say the events are positive and negative for whether the test tells me I have the disease or not. But just don't forget that these are, these are complements. And so that, for example, if I have the disease, given that I have the disease, the probabilities for positive and negative have to add up to 1. Okay, so what are these probabilities, right? These are each conditional probabilities. Conditional on having disease, what's the probability of positive or negative tests? Conditional on not having the disorder, what the probability of positive or negative tests? And let's write that as probability of positive given disease, probability of negative given disease, and so on. Right, these were given on the first slide, that in the instance that I have the disease, there's a probability of 0.99 that test comes up positive, correctly identifying this disorder in me, given my blood test. And what is left over here? What's the probability of a negative test given I have the disease? Well, they're complementary, as I said before. So that's going to be 0.01, right? And then in the event that I do not have the disorder, in the 999 out of 1,000 chances that I don't, if I'm in, as I very likely am, in the non-disease condition, given that information, what's the probability that the test comes up positive, incorrectly telling me that I have disease? Just 5%. What's the probability that it correctly tells me I do not have the disease? 95%. Right, and those add to 1. Okay, so we could, notice that the the probability of the probability of having the disease and testing positive, given that I have the disease, right? We can think of as the probability of positive and disease, right? In fact, we've well, that's the probability of the intersection of them, right? The probability of both occurring. We can't just multiply probability of disease times marginal probability of positive. We need to apply this more general rule for multiplication. Probability that both are true is probability of disease times probability of positive given disease, right? That is multiplying 0.001 times 0.99. And that comes out to 0.00099. We can do these for all of them. What we're actually calculating, right, is the probability of taking the entire 2-step path, right? Probability of having the disorder and testing negative given that I have the disorder, right? Or probability of both, right? So the probability that I have the disorder and then test negative, incorrectly told I do not have the disorder, is the product of the two. And that's 0.00001, right? Just 1 in 1,000, I think 1 in 100,000. Yeah, 1 per 100,000 will have the disease and yet test negative for it. And all of these intersections, I'm calculating the probability of going down this path of not having disease and yet testing positive, excuse me, is 0.04995, so about almost 5%. And the probability of not having disorder and correctly being told by the test that I do not have the disorder is 0.94905. Okay, so asking this original question again. Having tested positive, what's the probability that you have the disorder? Can you tell from what we have already that maybe our original intuition isn't quite right? Right? What do we have here? Given that I tested positive, which I'm somewhere. Wait, so I'm either here, right, where I have the disorder and tested positive, or I'm here where I don't have the disorder and yet I tested positive for it. And so I'm in one of these situations and I want to judge, what's the likelihood that I'm in the bad situation where it's indicative of having the disorder. So probability of disorder given testing positive. Right, I've gone down one of those paths. Probability of disorder given positive is probability of disorder and positive divided by probability of positive. I can rewrite the numerator as probability of disorder times probability of positive given disorder. The denominator, probability of positive, well, it's the probability of positive given the disorder weighted by the probability of the disorder, right? We already have it. It's 0.0099, right? It's that, or the ways that I could be testing positive are that I either went down this path, which had a 99 out of 100,000 chance of happening, or I went down that other path that led to positive, which was the almost 5% chance. Right, and what I'm interested in, well, there's the 0.0099, and there's the 0.04995. Together, the sum of those, that's the denominator, because I'm constraining. I know already that I tested positive, so I'm in one of those two states. So the denominator is the sum of those two numbers, 0.05094, but what's the numerator? It's just the 0.00099, right? And so the probability that I have the disease, given that I tested positive for it, is just 0.01943, or just under 2%. That should be surprising, right? It seemed like we had really strong tests. What's going on here? Well, you got to balance this against the fact that it's a very rare disease, right? So why is our intuition so bad? Let's just look at it quickly from another point of view. Let's make it concrete, not even think in terms of proportions or fractions. Let's just suppose there are 100,000 people, and we'll break it down. We'll use the proportions, but we'll think with how many people are in different situations, right? So if 100,000 people have it in all, then 100 have the disorder, right? If it's 1 in 1,000, and so 99,900 do not have it. Suppose everyone gets tested out of these 100,000. Of those who have the disorder, how many tests are expected to come out positive and therefore correctly telling them they have the condition? 99 out of the 100 with it will be correctly diagnosed. Hey, you have it. One is going to incorrectly be told that they don't and have an undeserved sigh of relief. Okay, of those who don't have the disorder, how are the tests going to come out? Well, most people don't have the disorder, and 94,905 are going to correctly be told that they don't have the disorder. And yet right? What about the 5% of that are incorrectly diagnosed? 4,995 are getting misdiagnosed and being told that slide cut off, but they're being told that they have the disease when in fact they don't, right? So the problem was that there are so many people without the disease that just 5% works out to 4,995, whereas there's so few people with the disease that there's 99, even though most are correctly diagnosed, that 99 with positive tests among those who have the disorder compared to the 4,995 healthy people, right? So a small percentage of a large number here winds up being bigger than the high percentage of a relatively small number. It's not always the case, but it was here. So we've got this test coming back positive. Of course, if it's a it's a genetic disorder that is dangerous, that could have dire consequences. I am, even knowing this, going to be fairly nervous. Why? Because I went from a 1 in 1,000 chance to now a 1 in 50 chance. That's bad. I'm worried, but it's not correct to think, oh well, those tests are great. I basically likely have it, right? And that can sometimes be a misunderstanding even with doctors, if they think, hey, these are good tests. And but if it's for something that's very, very unlikely, then you very well may have more of it, still a higher chance that you don't have it, even though it came out as a positive test. So again, if you're among those who tested positive, and in this case, means you're among the 99 with the disease who tested positive, and the 4,995 who tested positive who don't have it. You're somewhere in that 5,094 who tested positive, but only 99 out of those 5,094 have the genetic mutation. So it's very unlikely that you have it.